Today we will cover this paper, Deep Equilibrium Models, which was proposed by the researchers from Carnegie Mellon University. And today we will learn how to match the performance of very deep models for sequential modeling with using just one implicit layer. So the outline for today's talk will be the follows. First, I will introduce you the problem. Then we will consider how this problem can be solved with deep equilibrium models. Then we will consider experimental results, and discuss the properties and potential limitations of the approach, and discuss how it will be generalized. So we start with considering a sequence modeling task. So basically what we have is some inputs x, which are sequential and have the shape t for the time axis and embedding size p. And the outputs of the model is the sequence 2, so it's like a many-to-many sequence model, which is constrained by that for each output y t, it should depend only on those x's from time 1 to t. So in applications for such models are language modeling and some time series and many more. So it is like a common knowledge that people like to use very deep models for various tasks because they can use some features from previous layers and combine them in various ways. So the known limitations of using very deep models is that the number of activations which you need to store when you're doing forward pass for your subsequent backward pass is proportional to the number of layers of your model. So, and this is the problem. For this problem, there are known solutions. For instance, it's the gradient checkpointing when you want to reduce the number of activations which you want to store for your backward pass, using such a sparse scheme for storing these activations and doing some additional forward passes to restore the activations for the backward pass during this backward pass. And this is using this scheme, we can reduce the number of activations by the root of the number of layers. And there is also an approach which was discussed in the previous seminar, the neural ODEs, which actually don't need to store all activations on the forward pass for the backward pass, because it is kind of restoring it during the backward pass using these black box solvers. And the approach we will cover today will be kind of similar to the narrow ODEs approach. So consider a common deep sequence model. There is a number of layers, and there is an X, your data, which you usually feed to your sequence model. So, and each layer usually consists of there is a variable parameter for each layer. So there is some function f1 for the first layer and some function fl for the last layer, and they are different. And there are these activations that the outputs of our layers. So we will use this notation today. For today, to introduce deep equilibrium models, we will consider a different type of models today. White-tight input ejection deep neural networks for sequence modeling. So the change is the follows. We now have this Z0, which is like an initial state which we use applying some functions f with parameter theta to makes some last state ZL from it. So it's more like we have this initial answer Z0, and we will transform it to get an actual answer ZL. And the difference from the previous model is that we use the same weights and the same functions f for each layer. And also we will inject our input x in each layer, for example, adding it as a parameter of the function f for each layer. So it's not like this might have happened after I moved it to this computer. So sorry for this blur. I don't think that we can fix it now. There is an architecture that was recently proposed. It is a convolutional neural networks with white-tight weights and with input ejected to each layer. This consists of these blocks on the right. So basically, you have your layer layer I, and for each state, each state of the layer is actually depends on two states from previous layer. So it's from this point, it's like a temporal convolutional network, and actually this model have some connections with recurrent network. It was proven in an original paper, and this activation function, which is this red circle, can be some recurrent LSTM cell. So this model is kind of from one point a convolutional network, and from other point a recurrent network. And also we will consider today a transformer network today. Somehow this picture is not blurred. So you all know the basic transformer architecture, but this is the universal transformer, which has a difference that all weights are actually tight. So it's like you have some initial representations one more time, and the transformer block from the original transformer is updating these outputs in a recurrent manner. But usually, transformer architecture is not written in the form of with injected inputs. So in the paper, input X were added just with positional embeddings to this model. So now we are ready to consider the deep equilibrium approach. So we have these layers of our network which are applied in this recurrent pattern of updating initial state Z until like we obtain some good answers for our task. So the natural question for now is to ask what is the limit of such approach. If this limit exists, we will name it an equilibrium point of our model. And so, and I'm sorry one more time for this. It was unexpected. So we have these graphs. I will just explain to you what was in there. So we have these graphs which empirically show that actually if we take our trellis network on the left and transformer network on the right and consider applying many layers to it, say 500. And we want to know if the difference in outputs of last layers are kind of the same. So if these outputs converge to 0, that means that our after stacking many layers, we finally get our equilibrium point. And so it was like seen, its initial motivation, these outputs actually converge. So how this can be useful for doing our training faster? So imagine now that we can somehow reliably get our equilibrium point, for instance, stacking an infinitely many layers for our networks. So what can we do with it? So Z0 is our equilibrium point, the output of this very deep network. And let's denote this like this parameters of our function f, which is our layer. So the function f depends on our current output of the model, and it depends on inputs which were injected. And so we write here an equilibrium equation, meaning that our Z0 equilibrium point is not changed after we apply a layer one more time. So and then we apply here an implicit differentiation theorem, meaning that we consider our output Z the function of our parameters, and we differentiate these equilibrium equations with respect to parameters and get the following. So on the left part, this is the derivative of the output equilibrium point with respect to parameters. And on the right part, there is a direct derivative of our output with respect of our function f with respect to parameters plus the derivative through our equilibrium point, which is derivative of our function with respect to equilibrium point times derivative of equilibrium point with respect to parameters. And so actually the green underlined things are known for us. The first green part is just a derivative of our layer with respect to its parameters. And the second part is the derivative with respect to its input z. So these parts are known and can be calculated just with Bartosz's autograph. And the right part and the red parts here we want to know. So if we want them, we can do backprop actually, because this is derivative of the output of our network with respect to parameters, and we can just rewrite it in this form. And so this is the same equation, and let us denote this function z, introduce this function z, which is the difference of f of equilibrium point minus equilibrium point. And actually this thing of which our derivative is multiplied is just a Jacobian of the function g at the point or at the equilibrium point. And so plugging it here, we get our expression for the derivative of equilibrium point with respect to parameters. And actually, that's it. So we somehow managed to do derivative of our output with respect to parameters not considering the way that this equilibrium point was obtained. So we will not do backprop through all these layers of network. We just do the backprop using this equation.
But it's a bit strange. So we're not using the activations from the previous layers, for example. Is it okay?
Well, we don't want to know how this equilibrium point was obtained. We just want to write this equation and get what we want.
So this means that if we know that we converge to equilibrium point,
yeah,
then we do not need to perform any kinds of backpropagation. All we need to do is
just to solve this equation. And yes.
The strong assumption is that all of your layers are the same.
Yes, this is under the assumption that all our layers are the same. Yeah.
And do we also need additional assumption that after we change our parameters, say our theta a bit, we are still guaranteed to converge to the equilibrium point? Because it may happen that we have equilibrium point, but if we change the parameters a bit, we will not have an equilibrium anymore. Then I guess that this is
we will discuss some properties of is this equilibrium is stable later. But spoilers, for transformer network and for trellis networks, there is no these theoretical guarantees. So it's just more like an empirical observation. But I will talk what we know of guarantees later.
I see.
Mm-hmm. So we have this equation. If you have some questions about it, ask them now, please, because we it's like the main idea of all the.
Well, this is a very good idea. So now I understand why the paper was accepted as a spotlight presentation. So we have very deep network, but we do not need to perform backpropagation anymore. If we know that we have reached the equilibrium point. So this is a very elegant idea.
It can happen infinite number of computation instead.
Yeah, but we will not need this infinite number of computation. Now I will show how we can this equilibrium point faster and more reliable. So yeah, this is just how we will derive the gradients of our loss function with respect to parameters of the network. So we just have this guy was calculated from the previous slides, the derivative of the equilibrium point with respect to parameters, and we just plug it here. So that's how our SGD update can be performed for this model. So actually, for obtaining the equilibrium point, they don't do this kind of stuff with stacking and infinitely many layers. They just use any black box root finding method for it. So what all we want to do is just solve this equation so that f of equilibrium point minus equilibrium point is 0. So if we can solve this equation reliably, we got our method for finding these equilibrium points. So, and they used a quasi-Newton method for solving this equation, Broyden method. So this is an iterative scheme for this method. We have some initial Z0, and we update it with an iterative scheme of the Broyden method using the following expression, where B is an approximation for Jacobian inverse of function Z or of function G, and alpha is the step size.
One question. Are we guaranteed to have just one equilibrium point for the QNX?
So for these models, trellis network and transformer network, they had actually one point. So they were, when they were using Broyden methods, they were getting the same point. They were obtaining staking many layers, and but like theoretically, we need like our function to be conjective, so we need some contractive, so that we ensure ourselves that actually there is a unique solution for this equation.
Can we guarantee that Travis and transformer networks model contractive metrics?
No. There is just
traditional restriction cell activation function.
There is like a known thing for them that they have these layer norms, and so some kind of functions there which restricts, which makes them more contrastive, but like the strict proof that they are contractive is, no, we don't have it now. So on in this graph, we potentially can see why the Broyden scheme is actually good for us. So what we have here is on the x-axis is the number of function evaluations that we do, and on the y-axis this is the difference between the last adjoint layers. And so the blue line is the plot for a transformer when we just take many layers. This is for epoch 12. So, and the the orange line here is what we got using Broyden method. So just Broyden methods, using Broyden methods, we get this equilibrium point more reliably, but this is just an empirical observation. So actually our scheme for method looks like this. For a forward pass is just a root finding method using which we obtain our equilibrium point Z. And the backward pass looks as follows and was discussed previously. So, but actually they don't store these Jacobian inverses and don't store Jacobian matrices. Instead, they estimate this thing by solving this linear equation. So there is an x here which is unknown from the system, and solving this linear system of equations, we obtain this thing on the upper. So, and for this system of equations, all they need to have is to use a fast vector Jacobian product from autograd, which is efficient and we don't actually need to store these large Jacobians here, just a vector Jacobian product. So now we are ready to see some experimental results for the model. So they were experimenting on 3 data sets for sequence modeling. First one is a copy memory task, when you need to copy a sequence of digits and before some delimiter. After this delimiter, where previously were zeros, and you need to set zeros before the delimiter. So this is just stress test for which RNNs were proven to solve this kind of poorly, but this model will do better. So, and second is the Penn Treebank data set for word level language modeling. This is a medium-sized data set with vocabulary size of 10,000. So this is data set without punctuation, without capitalization, without numbers. And the third data set is a much larger corpus, which was obtained from Wikipedia, and have a large vocabulary size and no punctuation retained and no numbers retained and capitalization. So for copy memory tasks, they actually solve it far better than LSTMs on the sequence lengths of 400. And
what was TCN?
TCN is a temporal convolution network. And for Penn Treebank, they show that if they take like a 16-layer trellis net with the same number of parameters as a 1-layer deep equilibrium trellis net, and actually they show kind of the same results on this data set, which are very close to state of the art, and the deep equilibrium trellis net need much less memory than its multi-layer trellis net counterpart. And for Wikitext, they use the same comparison where they fixed the number of parameters of the models, and they show that for a transformer network, for a trellis network, they have the test perplexities kind of really close to state of the art too, and actually they are comparing to gradient checkpointing tools, and so the memory they need for the training is less than for the models, multi-layer models, and for the models with gradient checkpointing. But a problem here that these models are kind of slower than the multi-layer counterparts. So it's like the same problem, I think, that for narrow ODEs. So they actually, on the average, need, say, 2 or 3 times more time to obtain an equilibrium and to do backprop. So, but actually, and also there is a problem with mini batches because, like for some x, the model need one number of iterations of this root finding scheme, and for other x it need more iterations. So kind of if you have a fast x in your mini batch, and so it's need to wait until all x's in the mini batch are calculated. And actually, you don't need for these models to use like a very low tolerance for your Broyden methods. You may want to increase your tolerance, so trading your precision for speed here, and on average you will get something around 1.5 time for your model. So in this graph, it is on x, it is the tolerance that you have, and on y, it is the validation perplexity. So when you start to increase your tolerance, you still have kind of the same perplexity, but like if you increase it too much, your model will just, yeah.
And what is tolerance here?
Tolerance is from the Broyden method. It's the norm of your G. So it's like how close to 0 you want your.
I see.
So, like the natural question to ask here: do we have the same equilibrium points like always, and what are the guarantees? So there is another paper there which try to pose, which try to set some conditions. So we have here our equation for equilibrium, which is our state equals some nonlinearity function over a linear transformation of the state plus some constant. And they pose some sufficient condition of a matrix A. So if your nonlinearity phi is contractive, which can be like ReLU activation or some other types of activations. And so what are the sufficient conditions for the matrix? So basically, they prove that an operator norm of this matrix should be less than 1. So meaning that for, let's say, L1 norm, your maximum in each row should be less than 1. And for L2 norm, your maximum eigenvalue should be less than 1. So in this, like a contraction for you to have a unique equilibrium point and have some guarantees that you will converge to it like always. So
what do you mean by uniqueness here? Do you really need uniqueness for your transformer for each?
you mean we can maybe want to have some different answers here? Yeah.
Yeah, of course. We need different fixed points for different inputs.
Yeah.
No, but for fixed input, we should have just unique equilibrium point.
Either we have a unique equilibrium point for one input, or we do not have an equilibrium point. How can there be two different equilibrium points for one fixed input?
So this is a good question. Maybe we actually do once multiply equilibrium, but I think maybe if our equilibrium point is like not unique, our iterative scheme for Broyden method might not converge, or like we will have very many possible equilibriums, so we will have a big error for like.
So I really don't understand what does the uniqueness mean, because
Yeah.
from a mathematical viewpoint, if you start your iterative scheme with fixed points and you just repeat the same step all the time, then you're guaranteed to come to one point or not to converge.
So they just show that they have a unique point for transformer network and trellis network, but maybe you're right, and we don't need this condition to successfully apply this scheme.
Yeah, but at the same time, from the 5 viewpoint, due to some numerical instabilities, even though the scheme converges, it can converge to different points. Maybe this can be a problem.
Maybe I don't have the answer if this is really a problem. So, but I think maybe you're right.
I guess the uniqueness is about that equation, that x equals to phi of ax plus b. This equation should have unique solution, because it may have potentially several solutions. But if those conditions hold, then the solution will be unique. So it's uniqueness about this equation, not about the multiple equilibrium points of our transformer networks for trees.
Is this result applicable to our case when we're interested in, for example, language modeling?
Your phi function is like a very small neural network, and here you can prove that this very small neural network will have an equilibrium point with these conditions. And you can like hope that your very big neural network will have an equilibrium point with similar conditions.
I think that probably the answer is following. Of course, if you just compute your output of your recurrent neural network or your transformer network in the usual way, you will converge to just one point, or you will not converge. You can't converge to several points. But if you use this fixed point equation for trying to compute the output, then potentially using different initial conditions, initial approximations, you may converge to different points. If there is not, if there are no guarantees for uniqueness of fixed point. So this is it. If we have guarantee that we have just unique fixed point, then instead of performing forward propagation, we may just use fixed point equation for computing the output. And this was the ideal debate. That instead of performing forward propagation, we are using fixed point equation.
So in your explanation, what is the factor that changes? Is it the input of the network or
The input of the network is fixed.
Okay.
But even if the input of the network is fixed, if I using fixed point equation for computing the output, potentially we converge to different points. And if I have guaranteed that the fixed point is unique, then we will converge exactly to the point which is the output of our network.
Okay.
I think there is some addition confusion here. If you remember the picture for like Treebank network at the beginning, there was Z coming from the bottom and X as features. So if you think of X here as Z there, then it kind of means invariance to your initialization of the scheme, to where that X is a parameter.
Yeah, X here is that. Yeah. So X here is inside B. It's like it's inside this B, so it's like a constant in our layer.
Am I right that this theorem just for like one layer neural network with say ReLU or sequential calculations?
If you somehow prove that your like box layer, which consists of some multiple steps, is contractive, this is still applicable. So your nonlinearity phi may not be a ReLU function, maybe some kind of transformer block or something.
Now, if we multiply ReLU function by 2, it will not be contractive mapping anymore.
Mm-hmm. Yeah.
By the way, what about the previous paper? Do they use any special initialization to their parameters trying to satisfy similar
Yes, they like they didn't find they used like normal initialization with low magnitude. So they basically were initializing from a normal distribution with variance like 0.05, something like that. So they empirically shown that this initialization is enough for network to be stable in that sense.
Well, but if you do such initialization, it has nothing in common with the maximum eigenvalue, even with a small variance of the normal distribution.
Yeah, but this theorem is. I don't think it's that we can just apply this theorem for our transform network, meaning that some other theory should be included here. So it's just a very like, simple theorem, so it's not very powerful. But in the paper of deep equilibrium models, they were actually trying to show that the restriction they have on the network, which is that it should be like white tight, input ejected. So they tried to show that it's not like a really big restriction. So by introducing this theorem, but it's really not really convincing. So what is going on here? We have like some feed-forward network on the left, where input x is fed in your layer, linear layer with some nonlinearity, and after that your Z2 is fed in another layer and another layer. So and on the right, they actually take all the matrices from all your layers and put it in this low diagonal shift operator, so that applying this big like weight matrix to your initial state, you using a white tight network, you will get the same results as if you were applying like this feed-forward network. But here we like get this linear blow up, so our matrix V is like really big, and this is actually not what we want for our deep equilibrium model, since we want to use like very deep, potentially infinitely narrow networks. So it's not very convincing, and potentially some more theory about how actually restrictive we are when using these white tight networks should be like posed here. And this is almost the last slide that I have. So actually there are more papers from this group. They have different types of implicit layers, once for SATnet, which is the layer that solves a maximum satisfactionability problem in a layer, and so it solves this semi-definite program for needs. So it's the kind of relaxation for this problem. And using this layer, they learn some like logical structure in the data and apply, for instance, it to learning the rules for Sudoku puzzle. And there is also another paper from this group, which is OptNet, where they use a layer to solve this quadratic program and doing backprop to obtain the parameters and restrictions for this quadratic program. So they like doing a lot of this stuff. So this was the last slide that I have. So we learned how we can build a model that potentially matches an infinitely deep network using only one layer. And we learned how to do backpropagation through this model. But further research is needed for these models to like pose some sufficient conditions where we can reliably apply them. So now questions?
Can you please repeat the third point? So every feed-forward deep model can be made implicit. Isn't that only for models where we can write the equilibrium equation?
I guess yes, but if this like theorem is kind of convincing for you, you have a much broader like space of models for which you can potentially apply this. But actually, you need to transform your network to this white-tight input-ejected manner.
What is the typical size of the theta parameters?
In the experiments, they were matching these parameters to make the whole parameters of the network like the same as for multi-layer models. So I just have some numbers for this in application for the Wikitext, for instance. So the whole number of parameters for the DEQ transformer model is like 100 million. So I don't have the actual number for each parameter of the transformer network.
Does this mean that you're trying to solve this equation with Broyden method in 100 million of parameters set?
Yeah, I guess yes.
And you converge to the optimum in just 100 of iterations?
So they claim that yes.
Your graphs with the convergence rate.
It was tolerance. It was 10 to minus 7 in tolerance. That's kind of.
By the way, could you anyway return to this convergence graphs?
This one, yeah.
For the Broyden? No.
This one.
Yeah, yes. Why they have here linear convergence? Shouldn't be superlinear, because you just make a quadratic approximation to the function.
I don't have the answer why is this like this type of convergence.
Or this is just because they do actually an inexact solving of a linear system with coordinate matrices.
Yes, they do an exact. So maybe it's it's actually that maybe that they didn't pose a problem like right. So the Broyden method may need more iterations than it may need in theory for some good types of functions.
They approximate the Jacobian, right? So maybe it's because of that.
No. They do not approximate. They run the linear solver for exact equivalent times vector operator, but solve this for sure, in an exact manner, if you have 100 million of parameters, you can't run 100 million iterations
But
for
100
solving every linear system.
Was 100 million including
But
buildings?
I don't think that this graph was for solving linear system. I think that maybe was for training. When we find an equilibrium point, there is like not linear system for an equilibrium
Yes,
point.
it's
Yeah.
not linear, yes, but this the dimensionality of the system
Yeah,
is
yeah.
huge. So it's well, I'm sure that your theta is really 100 million of parameters, because I don't believe that we are able to solve such a huge system just in the 2 seconds that you show in the forward propagation time.
Yeah, I will check for that.
Maybe that's a GPU cluster.
TPU.
GPU.
Maybe.
Okay, any more questions?
Actually, the technical question, how this model can be applied for like the inputs of different lengths? So the sequence modeling frequently require you to be able to model different lengths.
You just split your sequence in the number of parts and solve it sequentially. So in the paper there is a part about it.
Okay, so let us thank the speaker for a very interesting talk.